Hello everyone, welcome to lecture 1 in fluid mechanics. Before we get to actual lecture note, I would like to introduce the textbooks that we are going to use for this unit. You can see the Fluid Mechanics Fundamentals and Application, 4th edition in SI units. This is the textbooks that it is used for this unit during this semester. I have provided you with the link and a promotion code that you can buy the ebook for 15% discount. If you would like to buy it, then you go to Canvas site, and then you will find the link to Macroil for buying these textbooks and the code for 15% discount. Before that, I should have said that if you need to see me face to face, then you can come to my office, which is building 27, mezzanine level, M07. That's my office number. And if you need to contact me via phone or via Teams, you can reach me out on 6304-5825 or via email that you can see the email address here. That's what anytime you can reach out. Okay, the first things is that, okay, why fluid mechanics? Fluid mechanics is obviously is part of many day-to-day activity we're doing, technologies, health, and defense. Many of them we use fluid mechanics. As you can see, in this case, for example, we have a case that it is showing the near sea water, and then in that case, obviously, you can see the fluid mechanics, how important it is. Aeroplane, how aeroplane perform during flight, takeoff or landing. Sending a shuttle to space, then you can see has somehow fluid mechanics attached to it. Submarine here, and then we have obviously many just hang on, pen, laser pointer. Okay, and then we have shipment, and then these are cases that we have fluid mechanics. When we go to river system and water and ocean, then we have we need to know the knowledge of fluid mechanics. Piping, even at residential or urban area or industry, again fluid mechanics we need to know. Energy, wind turbine, for example, artificial heart, and then dams for storage of water. In all these cases, we again use fluid mechanics. Again, in sports, you can see, why they make a golf ball dimple. In that case, then this is fluid mechanics knowledge behind that one. Why some table tennis balls are smooth, and then why tennis balls are made rough, or what the application and different flap on aeroplane wing is. These are the things that all are related to fluid mechanics. This lecture is two-part. The first part, we're just going through the objective of this part is to understand the basic concept of fluid mechanics and understand different type of fluids encountered in practice. Fluid mechanics, if we are talking about, if we're talking about fluids, fluid can be both liquid and gas. And when we're talking about mechanics, that means how it is a fluid responses to forces. The other thing is that if we want to subdivide them, we have fluid at rest, which we call it fluid statics, and fluid that are in motion, then we call it fluid dynamics. A first few lecture would be mainly focuses on fluid statics, and then we move to fluid dynamics for this unit. If we want to have a comparison between fluid and solid, we should look at the molecular structure of these fluids, both fluids and solid. And as you can see here, the solid are, molecules are well structured, as you can see this case. In liquid, basically the fluid, the molecules can go everywhere, and in gas, basically they again going apart molecules. But the difference between gas is that always gases, the molecules are like to be separated, but in fluid they are attached, but in not in an order way. And as you can see, fixed, moved around, and then random motion that you can see for the gases. Now, again, we want to look at more micro state of the flow. Then if we pour a liquid in a container, basically we'll find that we'll have the shape of the container, and we'll have a free surface that we will discuss this later. But if we inject a gas in a container, obviously they can go, due to random motion, they can go out of the container. Depend if we confine the container, then and push the gas through, it will cause pressure. Similar to consider a car's tire that we pump air in it, and then you can see the pressure goes up. Now, again, if we put the fluid under force, then particularly liquid, then let's look at how the force acts. We know that the force can have two components. One is normal, the one is tangential to the surface, and then the one which is normal, we call it normal stress, and we show it normally with sigma, which is normal force divided by the surface area. And we have shear force similar to this one, which is tangent to the surface, and then we call it shear stress. Now, if we place the fluid between two plates in this case, then you can see that in this case, if we provide force to the upper plate and pull it to the right hand side, then you can see this fluid, or the control volume that we consider, it will deform, because the molecules are attached to the upper surface, move with the speed of plate, and the one, as we go further down towards the second plate, which is stationary, then the motion will be reduced, and this is basically called shear strain. So we can conclude that solid resist and applied shear stress, while fluid continuously deform at force F. This is what's happening. Again, if we consider fluid, for example, if a uniform approach velocity coming, similar to when we're talking about uniform velocity, that means all arrow has same size. That means there is no difference between velocity. Once this uniform flow or velocity approaches a plate, due to friction at the surface, the molecule adjacent to this surface will have zero velocity, and then as we go further up, then the velocity will be increasing, and basically the velocity profile over the surface will have this form. zero velocity at the surface, while the velocity of uniform at the upper side, this is basically called boundary layer, because what's happening, the fluid is affected with the boundary at the surface, and the flow region adjacent to the wall in which the viscous effect are apparent, then we call it boundary layer. For example, if we consider from this point, which the velocity is 0, up to where the velocity, let's say for example this point, become same as that one, then this region is called boundary layer, because the velocity have been affected by the boundary which is here at this surface. And these can be formed in many different objects, depending in aeroplane wing, even when blowing over a building, this can form. Now looking at this one, for example, the velocity profile, again you see the boundary layer, this is an object that the flow coming this way as uniform, and then as you can see as we go further over the surface, the boundary layer is forming, and it says velocity profile due to the no slip condition as a fluid flow over a blunt noise. For example, this is called blunt noise, and when the flow coming here, then by using flow visualization technique, we can observe how the velocity profile look like. Sometimes it happens that when the velocity, for example, if we have a curved surface like this, and this is like blunt body, the flow coming this way, then the boundary layer forming up to here, then suddenly from here the flow is separated. For example, you consider a cube structure like a building, which is a cube. Then what will happen when the flow coming in one side of this building from the side wall, the flow might be separated from the building. This is called a separation point, which we will have cases which we will look at it later on. In terms of classification of flow, we can have various types of classification for fluid. We call it viscous, that means frictional effect are significant. When we're talking about viscous fluids, which is most of real fluid have viscosity, then this called frictional effect are significant, particularly when the fluid is in motion. We have inviscid flow, which is viscous forces are negligibly small. For example, looking at this plate in here, there is a plate in here which is moving, that one, flow coming as uniform, then reaching to this surface, boundary layer is forming, and then this we call it up to here is called boundary layer, yeah, as we said, because it is affected by the flow over this surface. Then after that one, the velocity are all uniform. This is called, this lower part is called viscous flow, because it is affected by the surface and frictional effect are significant. But from here upward, then there is no relative motion of fluid, then we call it inviscid flow region. Even the flow is moving, but because there is no relative difference in between different layer of fluid, then we call it inviscid flow. Similar things could happen at the bottom side, depending how we arrange to blow the flow over the flat plate, as is shown in this figure. Again, another type of classification, we call it internal and external flow. If a flow is bounded by a boundary, then we call it internal flow. For example, flow going into a pipe, into a duct, like an air conditioning system, flow in a river or an open channel flow. These are all called internal flow. We have also external flow, unbounded fluid. For example, if we have a ball and the flow going over that one, this is called external flow. When flow going over aeroplane, then it is called external flow. When flow going over a car is called external flow. When flow going over a plate is called external flow. And you can see this is, for example, external flow. However, the flow in this river is internal flow. Again, another way of classification of flow is incompressible or compressible flow. If we density in incompressible flow, that means density of fluid flow is constant and there is no change. For example, if we put water in a container and then push it down, then it won't compress like liquid, for example, water. But if it is air, then like a piston, you push it, you can, or air pump, you can see the flow is compressed. Then this is compressed flow. That means as we provide pressure, the volume decrease, then density also increase. Then in this case, we call it like a compressible flow. But in case of liquid, is an incompressible flow. What we study in this unit, most of the case, and I would say 99% of cases or even 100 cases, we're looking at incompressible flow. That means the assumption is that density of fluid is not changing with the pressure we're providing. But yes, there are cases that, for example, if you even in liquid you provide very high pressure, then obviously the flow may be compressible, which we looking at it later on with hopefully an example in tutorial. Okay, another classification in terms of state of flow, we call it laminar flow, turbulent flow, and transitional flow. Okay, first things in public when we talking about turbulent means everything moving here and there. But in terms of fluid mechanics, this is not how we define turbulent. Even, for example, if you stay next to a river and you see the water is clean, you can see the sand at the bottom of the river, then this doesn't mean that the flow isn't turbulent or flow is, because the flow is, you can call it the flow is calm, but it doesn't mean it is not turbulent. So when we're talking in scientific way in terms of laminar, turbulent, or transitional, we're looking at internal structure of flow. Okay, when suppose that consider a column of fluid like moving in a river, but they have different layer. Then if you inject a dye between this layer and there is no mixing of dye with the rest the surrounding fluid, we call it flow is laminar. That means highly ordered fluid motion characterized by a smooth layer of fluid. However, in turbulent flow, the highly disordered fluid motion is forming. For example, in this case, if you inject dye in here, you will see that quickly this dye is mixed with the surrounding fluid. Why? Because two layer of flow is exchanging momentum, that forming different like a lump of particle, that the motion is disordered, and then in that case this momentum exchange between different layer of fluid causes that mixing happen quickly, but still you may see the fluid is clean. That means you with your eyes you can look through and nothing happen. We will have one lab session which we do experiment on Reynolds apparatus, and then you will understand better what means by laminar, turbulent, and transitional flow. Transitional flow is a flow that between laminar and turbulent in that case. Then we call this one transitional flow. If I want to summarize this one, laminar flow is in the form that different layer of flow moving relative to each other, but there is no momentum exchange between different layer. However, in turbulent flow, there is a layer of flow when they move relative to each other, there is exchange of momentum. I give you another example. If you stay in 2Q, people stay in 2Q, and they move in one direction or opposite direction. Okay, in that case, if there is no interaction between these two rows of people, then this is called laminar case. And consider each human as one particle of water. Then if you have this one person in the queue hit another person in the queue, you can see the queue would change its order. That means basically providing exchanging momentum between different people. Then in this case, obviously for the fluid particle, similar things happen. Once there is a change of momentum between one layer to another layer between particle, then this is called turbulent flow. We have also another classification which is called natural versus force fluid. Force fluid is the one that, for example, we water in urban area or reticulation system. This is a force. We're using a pump, for example, or fan to provide flow through air conditioning system or water through reticulation system. However, if it is happen, if the motion happen naturally, for example, this is this is called natural flow. Suppose that you put salt water next to clean water, which is no salt in there. So in salty water, density is higher than clean water. Then if we have, for example, put both at the same height and then separated with the plate, then once we remove that plate, then what will happen is that the higher density flow is moving under the lower density flow. For example, if we're looking at, I just want to show you something here. Pointer pen. Let's say, for example, this is a wall, and then this is you have salt water here, salt water, and clean water here. Then both of them at the same surface. The density of raw salt is greater than raw clean water. Then once you remove this plate, this salt water, which is higher density, move under that one, and this will move over. Then in that case, the motion will called natural flow. Considering a river joining an ocean, river normally have clean water, and then at the ocean entrance, then there are two different dense flow, then the motion will take place naturally. This is called natural flow. Another type of classification which we have here is called steady versus unsteady flow. If the flow does not, the characteristics of flow such as velocity, depth, pressure, and so on, does not change with time, then we call it steady. However, if this change with time, then we call it unsteady flow situation, which is opposite to the steady flow situation. We have also classification of flow, which we call it 1, 2, and 3 dimension. Now you can see, for example, if you consider between these two red line, then we call it between this one, only the flow is changing in one direction, then this is called 1D flow. If the flow change in two direction, for example, one direction here and one direction there, then we call it two-dimensional. If the flow change not only in this direction, also normal to the page, then we call it, for example, three-dimensional flow as well. And these are what we study in this unit. Mainly it is one-dimensional flow. Okay, now these are some sort of classification of flow that it is necessary for us to know when we read different aspect of, we study different aspect of fluid mechanics, and also we sometimes investigating different type of flow, then we need to know. System and control volume. What is a system? A system is quantity of matter or a region in a space chosen for a study. For example, if I consider this area, then this is called a system. We have its boundary, which is broken line, and boundary surrounding area. Surrounding is outside, boundary is basically the border for the system, but this border can be fixed or can change. For example, consider this case. This case, the cylinder is here, and then the boundary is fixed, but after sometimes it can change. This is basically called movable boundary. Or we have sometimes a closed system or an open system. If there is no exchange of mass between boundary of a system, we call this one a closed system. Consider this is a system. Doesn't matter if its size change, but as long as there is no mass crossing the boundary of the system, is called closed system. Doesn't matter if energy exchange, that's no problem. It can consider as still as closed system, but the only definition we have for closed system is a system that mass is not crossing the boundary of the system. For example, this is an open system. Why? Because this is the control volume, but you can see as a hot water system. You can see cold water can come in, hot water can go out, then mass is crossing the boundary of this system. Then we call it open system. Or again, flow through this nozzle is called an open system. But one thing, this doesn't matter, but the most important things in fluid mechanics is that normally when we are studying, we consider a control volume, and then we investigate the energy coming in, energy going out, what velocity coming in, what velocity going out, what force is applied to this boundary, what force applied to another boundary. These are the things that it is important for us. If we read this one, open system or control volume, a properly selected region in a space, it is usually encloses a device that involve mass flow such as compressor, turbine, and nozzle. Both mass and energy can cross the boundary of a control volume. That means you cannot say a control volume is closed or open system. A control volume can be a closed system. It can be also an open system. And then this is the important things we need to consider. Control surface is the boundary that we consider. For example, this broken line, and this can be a real or an imaginary border, or that one. Sometimes it can be moved, like this piston, for example, inside the cylinder can move up and down. Then the boundary of the system can, or control volume can change. So control volume can be fixed or it can be movable, basically we can say that one. Another aspect that it is very important to learn in fluid mechanics is dimension and unit. And this is something that I have seen often. A student make a confusion normally, and then when they solve a problem in fluid mechanics, unfortunately the answer can be incorrect because the dimension and unit have not been properly considered. We have 7 fundamental or primary dimension and the unit that we consider. These are length, as you can see here. We have mass, we have time, and these are what we using normally in fluid mechanics. We talking. We have temperature sometimes attached to some of the problem. We have amount of light, and we have amount of matter, and we have basically electric current. These are the 7 fundamental unit that you may face or work with in different unit. For example, on heat and mass transfer, or then you may work with the temperature or amount of matter, for example. But as I said, in fluid mechanics, we mainly working with these 3 primary unit. Sometimes a temperature is also attached to them. Dimension that we say, for example, mass, length, and time. For mass, we show normally with capital M. For length, we show with L, and for time, we show with T. However, this is independent. These M, L, and T are independent of the system of unit that we are using. In metric system or SI system, which we use for this unit, and your books is mainly, it says specifically SI unit version, then it's called mass. Kilogram is used for mass. Meter is used for length. Second is used for time. However, for English system or units in English system, we use pound, kilogram, pound mass, which is basically what we use for mass unit in SI, which was kilogram. For length, we're using feet. However, for time, we use similar to SI unit, we use second, for example. Okay, now consider force is mass, time, acceleration. Then, sorry for that. Then, in that case, you can see we show Newton's second law, mass. Then mass is kilogram. Acceleration is basically velocity over time, which we call it meter per square second. And then 1 pound force is basically 32.17 pound mass. Feet per square second if we use, for example, in SI unit. That means in English, in SI unit, the unit for force, which is coming from primary unit, is called Newton, or 1 kilogram meter per square second. However, in English unit, the unit for force is pound force, which is 32.174 pound mass feet a square second. That's how. So this showing us that, okay, what are the primary unit, what system of unit we have. We have metric, we have also English system. What we use for this unit is English system, SI unit. This is what we using in this unit. In fluid mechanics and other engineering problem, all equation must be dimensionally homogeneous, meaning that, okay, this is a interesting things to look here. If you mix up, for example, salami with lotus, olives, and other things, then obviously you upset your stomach. So in in system of unit or for any equation, we need to be careful that the dimension are homogeneous, meaning that, for example, if you have A plus B plus equal C, that means dimension for this one and this one should be same and same for this one. You cannot have different dimension for this one, add up to this one, and then you get something else. So meaning the dimension for each parameter, each part of the equation should be the same. This is called dimensionally homogeneous, and we need to be always have consistent system, firstly consistent system of unit used for solving a problem, meaning that SI units should be used. You cannot mix SI with empiric or English system. Also, the dimension for each part of equation when they add up should be same. For example, dimension for this one and this one should be same and should be same as this one. This is called dimensionally homogeneous, meaning that if you're solving a problem in SI unit, it's still homogeneous, dimensional homogeneity should be followed. Otherwise, the answer won't be right. This was what we discussed so far for the first part of this lecture. Now we move to second part, which is property of fluids. And for this lecture and lecture 2, normally we focus on property of fluids before we go to other aspect of fluid mechanics in this unit. Okay. We have properties that we have, obviously mass, volume, temperature, pressure, density, and these are how they are shown. Mass with M, volume in this unit we show it with capital V. Sometimes in they show it in this way in some textbook, doesn't matter, but this is what it is. Temperature with T, pressure with P, and density with rho. And then, for example, we have, okay, if we consider half mass, half volume, these are called extensive property, but T, pressure, and density are called intensive property. What means by intensive property is independent of mass of a system. So means temperature, pressure, and density are independent of mass of a system. However, extensive property depend on the size or extent of a system, meaning if the size of a system is larger, a bucket of water, if you have like a different size of bucket, then mass on each one can change. So in that case, the size is bigger, mass is bigger. These are called extensive property. And intensive, basically temperature is independent of mass, mass of system, pressure same, and density same. We have also specific properties, which is called extensive property per unit mass. This is this one, which is cold. Now, fluid is a continuum. So what that means? That means property varies continuously. This is the most important things that we need to consider. One of the property is density and a specific gravity, which is used throughout this unit, and different aspects of this unit, density and specific gravity are used. Density is mass divided by volume. Let's say you have a container. It is certain mass in there, and it has got also a volume here. So if we divide mass of this by its volume, it's called density. So if water is in there, then mass might be different. If mercury is there or Hg is there, then mass could be different. Even the volume is different. So if we have same volume for water and same volume for mercury, obviously the density would be different. Why? Because mass of each one is different. For example, in this case, you may know already that density of mercury is 13.6. However, the density of water, sometimes we call it 1000 kilogram per cubic meter, or sometimes they call it 1. 1 means, again, you need to be cautious about the unit that you're using. If we're saying 1, meaning 1 gram per centimeter cubic, per centimeter cube. But when we're saying 1000 kilogram per cubic meter, you need to be careful how you're saying 1 or how you're saying 1000. The unit need to be attached to it as well. So what I'm trying to say, if we have 1 liter of water and 1 liter of mercury, density of mercury is 13.6. That means 1 liter of mercury is 13.6 times heavier than water. And this is how density is set. Now in SI unit, we have kilogram per cubic meter. We have also a specific volume, which is inverse of density, is called a specific volume, or in this form, 1 divided by density, which is cubic meter per kilogram, but it is less used. Density is important. Relative density or a specific gravity, which is normally shown by Sg, sometimes by lowercase, when you see the problem is solved. And this is very important to notice. What means if we consider density of a liquid relative to density of water at 4 degrees Celsius, it is called relative density. So relative density Sg, for example, again, Sg for Sg of a fluid is 13.6. What that means, this is the liquid, which is in this case Hg 13.6, and this is water, which we call it 1. For example, in this case, a specific gravity or relative density is 13.6, meaning that relative density of mercury in this case is 13.6, which is 13.6 times heavier than water. Okay, now if we have gas, then we normally should consider the relative density or a specific gravity of gases with air at a standard condition. But in many problems, they don't use air, rather they use water. That means even for gases, they consider for water as well. And that's how it is considered. But in reality, should be considered relative to air, but in many cases, they considering relative to water as well. A specific weight, we have also a specific weight, which is, this case is weight density, which is called gamma, which is rho times g. And this is another things that it is considered. For example, we say gamma for water is density is 1000 kilogram per cubic meter, times 9.81. Then in that case we have 9810. This is gamma. Yeah. However, if we're talking about density, only 1000 kilogram per cubic meter. So a specific weight is density times acceleration of gravity. In here we have density we have a specific gravity of few liquid or air. You can see water is 1 because water is relative to water. Blood is heavier than water, that means 1.06. That means this number, if a specific gravity is greater than 1, it is heavier than water. If it is less than 1, it is lighter than that one. Seawater, for example, this one. Gasoline is normally, you can see oily things coming to surface. Normally when they mix with water, then the density is lighter. Ethylene alcohol, then mercury is heavier, is going down. And different things. Wood is low, dense oak wood, for example. Gold is heavier, even heavier than mercury. And then bones, so for example, it has got a density of that one. Ice is lighter. That's why you see when you put ice in water, it comes to surface. Even it is basically from same is formed from water. Air is again this much. Okay, air, this is where I said why this is 0.001, because this is considered relative to air to density of water. Then in this case, as I said, then that's why you see this look like very small number. But if it consider relative to air, then it should also be 1 similar to that one. But this is where I said most of the cases, even for air, is considered relative to water. But you need to watch the problem and to see which one is given, how you should go, and how you need to consider. Density of ideal gases. You know the ideal gas is pressure times volume equal to a constant times temperature, which this constant is normally universal gas constant, which is this number, divided by molecular weight. And pressure also, we can, based on this one, we can say pressure is equal to rho RT. And then further, another form of ideal gas equation is again this one, similar to that one, MRT, because we talking about mass in this case, or PV NRUT. Then in that case, N is mass divided by molecular weight. And remember, the temperature is considered temperature in degrees Celsius plus 273.05, which is considered, and in English or English unit is called like a Fahrenheit plus 459.69. We normally don't use this in this unit, but sometimes if we're talking about gases, obviously temperature need to be used in Kelvin scale, which is how we're using. And when we're talking about gases, obviously these are the ideal gases. We don't have much concentration on this ideal gas in this unit, but we will have a couple of, you know what I mean, tutorial question which we will discuss it. That's how we need to know. This is one example that talk about density, specific gravity, mass of air in a room. And the question is that it says determine density, specific gravity, and mass of the air in a room whose dimensions are 4 meter by 5 meter by 6 meter at 100 kilopascal. 100 kilopascal is almost equal to 1 atmospheric pressure, which we will know this one later, at 25 degrees Celsius. Okay, assumption in here in this problem, a specific air can be treated as an ideal gas, and then property gas constant of air is this much, which is already given, and the density of air is determined from ideal gas relation. So we know that pressure is rho RT. Then from here we can rearrange this equation to rho is P divided by RT, and R is a gas constant and temperature is given in degrees Celsius. Remember, we need to convert it to Kelvin, and then the density would be this much. Very simple. Then a specific gravity, we said a specific gravity is density of gas relative to the density of water in most cases. Then in that case 1.17, which we have it from here, and then divided by the density of water at 4 degrees Celsius, which is this one, and then this is a specific gravity. And finally, the volume and mass of air in the room are, volume is obviously dimension multiplied, and then mass is rho times V, which we already know that rho is mass divided by V, and then it is 140 kilogram. Very simple things, but obviously it is important for you to know how these are work and how you can. Here we're talking about gases and how we need to treat that one. The other item that you need to know, and it has got lots of industry application, is vapor pressure and cavitation. Okay, first things you need to know, saturation pressure is the pressure at which the pure substance change phase at a given temperature. That means basically phase change happen. This is the saturation pressure. We have also vapor pressure. Vapor pressure is the pressure that exerted by vapor in phase equilibrium with its liquid at a given temperature. And then vapor pressure is identical to saturation pressure. Now, if you want to have a sense of what means by vapor pressure, then in that case, if you have a kettle and you just let it boil over the heater, then you will see after sometimes, if the lid is loose, then you will see that, okay, after sometimes, yes, water is get warm inside the kettle, vapor going up, but it still is not under a state of saturation. Then you're reaching to a point that near the boiling or during the boiling, you will see sometimes the lid is jumping up, making noise. That means this is the state that vapor pressure has reached to the saturation stage. That means whatever vapor happen, then obviously at the same time the part of it converted to liquid again. That's why when you're looking at the lid, you will see droplet forming at the base. Then in that case, basically from whatever is vapor, again converted to liquid. This is phase equilibrium basically. And this is the pressure. And why the lid making noise or jumping? Because the pressure is, if we close this system, the pressure will build up and go beyond what should be. Then the lid going up and release some of the pressure again due to its weight pushing back. That means there would be a balance between weight of the lid and how much vapor going out to balance the weight versus the pressure which is exerted to the surface of the lid. And this is what will happen. So Now, when we're talking about vapor pressure, in this case, we normally saying vapor pressure and saturation pressure, which is here. Now, saturation pressure or vapor pressure change with temperature. If, for example, temperature is -10, then in that case, saturation pressure would be that. If the pressure is if the temperature is 30, then vapor pressure is basically 4.25. That means lower the temperature is, lower the saturation pressure is. Higher the temperature is, basically higher the saturation pressure is. But what is the cavitation? Now, it is important for us to know that, okay, what means by vapor pressure, and then now we can translate this one to cavitation. Okay, if I want to say, consider this pump here. Okay, here we call suction happen, because when the propeller rotate, yeah, when the propeller rotate, pressure here would be very low. Okay, when the pressure here very low, basically suck the flow through the pump, and here the pressure would be, if it is inlet, then this is outlet, then pressure at out is greater than pressure at in this case. Now, in this case, okay, this is how a pumping system working. Now, imagine the pressure here goes, pressure in become lower than what vapor pressure. If this become lower than vapor pressure, then what will happen? If the pressure is lower than vapor pressure, then boiling start to happen. That means bubble start to form, meaning that in here what we will notice is that sorry, just let's get rid of these. Okay, what will happen? We said if the pressure at this point goes beyond if the pressure at this here okay, pressure at this point here become lower than or goes below than vapor pressure, boiling start to happen. That means bubble forming. Now, there are lots of bubble in here because the pressure is becoming lower. And then once this bubble move to where the pressure is high, which is here, basically what will happen? This bubble start to burst. Bursting the bubble in here will form a stream of flow, or sometimes in here will burst, which forming a stream of liquid, which this stream of liquid acting like a jet of flow. Then in that case, damage the propeller, and this is where cavitation is called cavitation happening. So what we need to do to protect that one, we need to make sure when we do our designing, make sure in this region the vapor pressure, the pressure or the low pressure or suction pressure does not go below the vapor pressure. Please note, that means pressure in here should not fall below vapor pressure. Otherwise, if this happen, bubble form, bubble move to here with higher pressure, burst and damage the propeller surface. And this is big damage and cost to many different industries. Now, If you look at the text in here, it is cavitation. It is a phenomenon which causes performance of a system drop and in some cases erode impeller blade. You see here impeller blade. When the liquid pressure in a system drop below vapor pressure, cause liquid vaporize. Where did this happen? In this point happen. As we explained, the vapor bubble collapse as they sweep away from the low pressure region, generally highly destructive, extremely high pressure. That means when this bubble move here, they burst and these cause damage here. To avoid cavitation, the pressure in the system should not drop below vapor pressure. And this is what we learn from this slide is that vapor pressure, what is the cavitation, what the damage cause, how we should avoid it. And this is what we need to know. Danger of cavitation in a propeller. The analysis of a propeller that operate in water at 20 degrees Celsius show that pressure at the tip of the propeller drop to 2 kilopascal at high speeds. Determine if there is a danger of cavitation in this one. What we need to check in here we need to check that, okay, this pressure in here, the pressure that we're talking here, should not be below the vapor pressure. So how we find vapor pressure here? So temperature is given here. We go to the table that we have, for example, in here. At 20 degree, the vapor pressure is 2.34. So this vapor pressure is higher than the value is given in here. So what that means the pressure at the propeller is lower than vapor pressure. Then certainly in this system cavitation will happen. To avoid cavitation, the pressure everywhere in the fluid should remain above the vapor pressure at given temperature. So vapor pressure, as we found from table, was 2.34 kilopascal. The pressure at the tip of a propeller is 2 kilopascal, which is less than the vapor pressure. Therefore, there is a danger of cavitation for this propeller. How we should avoid it? We need to make sure the pressure here goes above that value, which is vapor pressure, and then we stop vapor harbor. Some of the things that you have in your formula sheet, and always you need to be familiar, also it is this table, which is at the end of your textbooks and part of your lecture formula. You will have access to this page in your in your formula sheet, in your test 1, test 2, and final semester. These are the things that you need to learn how to use basically this table. As you can see, it shows temperature, saturation pressure, density of liquid, density of vapor state, and different. Some of it is used in this unit. For example, this is viscosity, which we're using, and then surface tension, for example, we're using. These are the column that we're using, and you need to be familiar how to use this table. Basically, if temperature is given, we go through the column that we are after that property and find what the value is. Always read the number in here, and this is very important. The information in here is important to note. Okay, now another things that we talk about compressibility. However, we have a coefficient of compressibility, or bulk module of compressibility, or bulk module of elasticity. Bulk module of elasticity you may have come across in the other unit, for example, structural analysis or statics or so on. This is basically same things. coefficient of compressibility or bulk module of compressibility, which is same as bulk module of elasticity. How it is defined? Basically defined through this formula here, which is change in pressure and relative change in volume. Or we can instead use relative change in density. Coefficient of compressibility represents the change in pressure corresponding to fractional change in volume or density of fluid while the temperature remains constant. So as you can see, this is basically when we provide pressure, the volume gets smaller. That's why you have a negative sign in here. The large value of K indicate that the fluid is less compressible, similar to solid, for example. For liquid is high, however, for gases it is low. At normal pressure, liquids are usually considered to be incompressible, and in almost all cases that we consider for this unit, we considered the liquid or fluid, or even for air, we considered them incompressible. We will have, I think, one tutorial question which is covering this slide, and I hope that you will enjoy what is discussed on that tutorial. Okay, summary of this lecture. This part we learn about extensive intensive property. We learn about density, specific volume, specific gravity, and a specific weight, which are important things. And we talk about like ideal gas equation, vapor pressure, and how it impacting cavitation and compressibility and module of elasticity or coefficient of compressibility. Thank you for listening, and I hope you enjoy and enhance this material, enhance your learning. Thank you.